Chapter 10, Bonding Principles. In Chapter 9, we talked about creating Lewis structures and having molecules bonded together, who you see which atoms are bonded to which other atoms, where the electrons are. What we're going to do now is take that, and we're going to see, well, what does that mean in a three-dimensional space? And so we're going to look at molecular geometries. Valence shell, that's the outermost electron shell, and that's where all the bonding occurs, and that's where we're going to get repulsion among pairs of electrons, and we're going to get shapes in 3 dimensions. So we're going to use VSEPR model, valence shell electron pair repulsion model. All right, let's break that down. Valence shell, so the outermost electron shell, pairs of electrons repelling each other. So we're going to get electrons, pairs repelling each other, getting as far away from each other as possible. And this is going to account for all of our different shapes that we can get from molecules. We're going to kind of put our molecules into 2 groups. Ones with no lone pairs of electrons on the central atom, or we're going to have molecules with lone pairs of electrons on the central atom. And just the idea here is that if we look at this picture on the bottom, we have our central atom. We have that bond being formed between here, say these 2 atoms, these 2 and these 2. And what ends up happening is these electrons repel each other, and they try to get as far away from each other as possible. And again, we have to think in 3 dimensions for this. All right. As far as repulsion goes, repulsion between electron pairs accounts for our geometries. Lone pair versus lone pair, those have the most repulsion because those are closest into the atom because they're not being shared. All right, so those are closest in. Those have the most repulsion. Then comes lone pair, bonding pair, and bonding pair have the least repulsion. We'll see that later on. All shapes are based off of the number of directions which electrons are coming off the central atom. So the simplest we'll start with is our linear molecule. It has this notation A, B2s. A is the central atom. It has 2 other atoms coming off of it. No lone pairs on the central atom. So 2 sets of bonding electrons. They get as far away from each other as possible. So what shape what's the angle between them? 180 degrees. That's as far away as they can get from each other. All right, so here's single bonds, our beryllium dichloride. Well, what about if it's a double or triple bond? All we care about is how many directions are electrons coming off that central atom. So in carbon dioxide, even though they're double bonds, it's still one direction to the right, one direction to the left. They get as far away from each other as possible. Hydrogen cyanide, same thing. Triple bond to the right, single bond to the left, they still get as far away from each other as possible, 180 degrees. So the shape of this, we would say, is it's a linear molecule. Pretty easy to remember that one. Next up, AB3. So that ends up being trigonal planar. Exactly what the words sound like. They're in a triangle. Planar, they're all in the same plane. So it's a flat molecule. All right, they get as far away from each other as possible. We get that 120 degrees between them. All right. Tetrahedrals next. AB4, so we have our central atom, this carbon, with 4 atoms bonded to it. So we would say, hey, what's the angle here? And you'd say 90 degrees. Why is that wrong? Because we live in a 3-dimensional world. So here, for them to get as far away from each other as possible, they end up being about 109.5 degrees from each other. Any angle between hydrogen, carbon to hydrogen is 109.5. Right, again, 3-dimensional. We draw it, it looks 90, but when we're thinking about the 3 dimensions, now it gets into that 109.5. Tetrahedral. Why is it called tetrahedral? Tetra means 4, hedral sided. So we have like a 4-sided object when we look at our the shape of this molecule. So next up, AB5. So now we're into our expanded octet, right? So anything from phosphorus and bigger can have this expanded octet. So phosphorus, we look here, if 5 things are bonded to it, that's 10 electrons around it. This one is called trigonal bipyramidal. So if I cut this right across the middle here, it looks like there's a triangle or a pyramid on the top and a pyramid on the bottom. And that's where we get this. It's a trigonal pyramid because it has 3 sides to the base, 3 points to the base. Here, all the atoms are equal. All right. Instead, we have the 5 locations. 2 of them on the ends are axial, so they form a line. The other 3 are oriented just like that trigonal planar is. And we call those the equatorial ones. So equatorial around the middle, just like the equator. And then we have our axes at the top and the bottom. That's AB5, trigonal bipyramidal. If we add one more, now we have octahedral. All right, why do we call it octahedral? Because now it's shaped as a pyramid with a 4-sided base. So we would have 8 sides to this one. All right, we have 6 atoms bonded. Excuse me, to the central atom. All right, something like SF6. All right, we have our center one. We have 90 degrees between all of them. So the ones in the straight line, the axial one's still 180 degrees. All right, so now what we're going to do is we're going to take those shapes that we just did, and we're going to replace one of the bonds with a lone pair of electrons. So this is called bent or angular. What we did, if this pair up here was another X, that would be our trigonal planar shape, right? We would have A in the middle. We'd have elements or 3 atoms coming off that central atom. Instead, we're going to replace one of those atoms with a lone pair of electrons. So that's AB2E. It was AB3, but again, we replaced one of the B's with a pair of electrons. All right, so what do we have left? These electrons come in, and now we ignore those. When we're saying the shape, we're just saying the shape of the atoms are forming. So we have the X to A to X there. That is a bent shape, so we call it bent. All right, trigonal pyramidal. This is based off of our tetrahedral shape, right? We had CH4 before, where we had an H here at the top, that 109.5 one. But instead, we take the bonding pair away, we put a lone pair on the top. So what's left instead of tetrahedral, we call this trigonal pyramidal. So it looks like a triagonal pyramid. If we're all right, if we replace the second one of these, all right. So picture we can picture in our head that tetrahedral where we have 4 bonds coming off that central atom, the 4 atoms. We replaced one. That gave us the trigonal pyramidal. We replace the second one. What's left is we have another bent shape. This bent shape has a smaller angle than the first bent one does, but we still call it bent. All right, and that's why this is a terrible drawing of water, the straight view, because again, 3-dimensionally, that's going to have that bent shape to it. All right. Without those lone pairs, then they would get as far away from each other as possible. It would be 180, but we have lone pairs, so we end up with a bent shape. So this is, again, why it's so important to draw the Lewis structure correctly so that we can figure out the shape correctly. All right, so here, these 3, we can kind of picture are all in the same family. They all have electrons coming off in 4 directions. They all have electrons coming off in 4 directions, right? Lone pair is still a direction. Bonding pair is still a direction. All right. Here we have our 109.5. Here it's a little bit smaller. Why? This goes back to that lone pair, coming in a little bit closer to the nitrogen and having a greater repulsion. So what does that do? That pushes the 3 bonding pairs of electrons a little bit closer together, and we get a slightly smaller angle. So we replaced the top hydrogen with a lone pair, which scoots themselves a little bit closer to the nitrogen and pushes those remaining bonds down. With water, we have 2 lone pairs. So that's going to push those and repel them even more closer together, and we have an angle down to 104.5. We don't have to memorize the exact angles, but we have to know that water is the smallest here. Our NH3 would be in the middle, and our methane would have the greatest angle. A little bit with drawing these, to draw them with some perspective, you see how this is like a triangle? This is showing this H is coming out of the board at us. It's coming out of the board. These ones that are just the regular bonds, those are in the same plane as the board. And this dashed line is going back into the board. All right, so this shows that it's three. This is trying to show that it's a three-dimensional structure on our two-dimensional piece of paper or our monitor. All right, here we have our first expanded octet where we replace one of the lone pairs with one of the bonding pairs with a lone pair. We said before that there was axial ones, axial bonded, and equatorial bonded. We always lose the equatorial ones first. We lose the equatorial ones first. So by taking these away, we get a shape that looks like a seesaw. And that's actually a technical name that we could use. We could use distorted tetrahedron. I think a seesaw is a little bit easier. If you turn your head, you can see how this would be our seesaw. All right, this is our regular tetrahedral, but if I put a lone pair of electrons right down the bottom here, that's going to straighten it out, and we end up with our seesaw. Here's our upside down seesaw. I replace a second one of those bonded atoms with a lone pair of electrons. Again, it's from the equatorial ones. What's left over? I have a T-shaped molecule, so we call it T-shaped. If I replace all three of those equatorial ones, I'm left with just the axial ones. I now have a linear molecule. So it's another one with a linear. The first one we learned was linear, that had no lone pairs. The three lone pairs keep those fluorines away from each other, and we end up with another one that we can get as linear. All right, square pyramidal, this comes from our octahedral. All right, we replace one of them with a lone pair. Now, all of these are equivalent to each other. There is no real axial or equatorial. So we just replaced one of them, and now it looks like a square pyramid. So it's square pyramidal. An example of it. If we replace the second one, now we have square planar. These two lone pairs keep those four fluorines in the same plane. It looks like a square planar. All right. All of these are kind of have a, I don't want to say a buddy, but like they're within a system that we have to learn. It's not 20 different shapes. It's really about 5 different shapes. And all we're doing is we're taking atoms away and replacing it with lone pairs of electrons. All right. So again, we have our linear. That's electrons going off in 2 directions. So this particular graphic calls it charge clouds. There's 2 charge clouds, electrons coming off in 2. Here, there's 3. So we have our trigonal planar, electrons are coming off in 3 directions, or we can replace one of these with a lone pair. Still has electrons coming off in 3 directions. Now we have our bent molecule. All right. 4 directions, we have our tetrahedral, replace one with a lone pair, trigonal planar, replace the second. Now we have our bent. So that's like kind of like a different family there. 5 charge clouds, we have our trigonal bipyramidal, replace 1 is the seesaw, replace 2, the T-shape, replace all 3 of the equatorial ones, we now have a linear molecule. The last one is 6 charge clouds. We have our octahedral, replace 1 square planar, replace 2, square pyramidal, replace 2 square planar. Excuse me. I think we have something like this in our, again, same idea. We have this calls it electron pair geometry, going out in 2 directions. If there's atoms there, it's linear. 3 directions, trigonal planar or bent, tetrahedral, then we get it. So all of these are in our different groups that we can kind of put together.